We'll start. So, my current plan is I'm going to hop on Zoom tomorrow with all the TAs, give them directions on how to grade the exams, and then they will grade the exams. If you have issues with the way they have graded the exam, you come and speak to me. Got it? I am more than happy to say, oh, that was a bit too strict, and give credit. If for some reason something has happened, or you did poorly on the exam, remember, we will have 3 midterms and a final. I'm sure you're wondering when those are. 3 midterms and a final. Those will be, and we'll be taking the best 2 out of 3 of those. So if you completely botched this first one, there are 2 others you can still do. Your second exam, I know we just got done with the first, but that was not my intent. My intent was to be done with the exam here, not here. Your second exam will be week 11, currently week 8, 9, 10, so 11. So it would be it'd be April 3rd and April 6th. 3rd is the second day of Pesach. April 3rd, I believe that is the second day of Pesach, since Erev Pesach is Wednesday evening. If that is an issue, reach out to me. And we can just reschedule. That's easy enough. Same with any other religious conflict. And we'll most likely do proposal day, I guess, on the 7th. We'll figure that out. I'll get into that later, but in about a month we'll transition to working on the final project. We'll start on the 21st, or in a few weeks, we'll start going over kind of the ideas of the pre-proposal lab, which is basically where we start thinking about the ideas and brainstorming. The proposal is this part where you come to me and say, oh, this is my idea, actually. Okay? So, actually, most likely that will happen on the 2nd, if I'm going to... All right. Right, other things. So, Runestone. Those of you who happened to check it yesterday noticed I may have started running the grader for it in the afternoon. Tonight or on Wednesday, I will be importing your current Runestone grades into Canvas. This will give some of you a mild heart attack, because you'll have a bunch of zeros because you didn't do that, because you didn't keep up with the readings or whatnot, right? I want to emphasize here, okay, because it doesn't matter how many times I say it in class, the people who are not here are going to still send me the emails saying, hey, can I please make up the late work? Those zeros are all fixable. It's just simply what you currently have, and it serves as a very non-gentle reminder to keep up with your readings. Make sense? But that import will happen, and you'll basically get a bunch of emails all at once saying that I've changed a bunch of your grades. That happens. If it's wrong, don't freak out. Just let me know. Because there's a few different ways that can go wrong. I suppose now's as good a time as any, now that since we've been talking about file reading. So you see, what I do for the grader is that I have 2 CSV files. These are from last semester. I can't open them and show you because that has students' grades in them, and that would be, I can't show grades. It's actually against the laws, privacy laws and stuff. Okay? So I have these 2 textbooks, 2 grade books, one from our textbook, which is Runestone, and one which is Canvas. And I got to merge them together. The issue is it's a pain in the butt to match up one name to another and copy paste all the fields over, right? That's actually not fun at all. So we use a script to do that. And let's see. Let me open Geany up, and this is my script to do that. Okay. So you don't need to know what import CSV does. It's honestly, I could do it without import CSV. It just made it a bit easier. We'll be learning about these on Thursday, these curly braces, which are called dictionaries, or if you're coming from another programming language and happen to get to them, hash tables or associative arrays. Okay? Think of them as lists, except that anything can be an index. Okay? Such as a name. So I create one called a hash and then one called emails. And what I do is I open up the Runestone textbook. This is a newer, different way to open up a file, but it's unnecessary to do it that way. I could have just done it with open, without the with statement. But basically, this is saying Runestone is equal to Runestone is equal to open Runestone CSV. Create a CSV reader. I just read it and turn it into a big list. I get rid of the first two rows because those first two rows are basically headers. And what I do is for each row, I grab the name, which is in, and put it into the same order as Canvas does, which is to put the last name, comma, first name. Okay? And then I capitalize it and remove any extra spaces you may have accidentally entered. And then what I do is I look for your email address, your TU. I look for whatever email you put in, hopefully your TU email address, right? And what I do is I take that and I basically make that the key for your name. So basically if I say, hey, give me the name, so Rune emails, what it will do, as we'll learn on Thursday, is it will say, hey, if you give me the email address, I'll give you the name associated with that email address. Okay? So I set it up so I can do that. And I also set it up that if I give this variable, the Rune hash, the name, it gives me everything in the row from column 4 and onwards, which is to say all the numbers that are associated with your grade. Okay? So basically, I have a way to look up your name from your email, and if I have your name, I have a way to look up the rest of your grades from Runestone. Then I create a new file to write, which is what I'll be uploading to Canvas. Then I open up a way to read my Canvas file. And then for every row in the Canvas file, I grab the name, right? I strip any extraneous spaces from the beginning or end. I get your TU ID, the TU whatever number, okay? And I add @temple.edu so it becomes your email address, okay? And then what I do is I ask, hey, do I have your name? Do I recognize your name as one of the ones that I stored? If so, I just add all the stuff from the Runestone grade, from the Runestone grade book to the end of the current row. Make sense? If I don't have your name, I ask, do I have your email? And if I do, I grab your email from your name. So I grab your name from your email, and then I go and I look and I put that together. Sometimes this happens and it helps, where basically I say, hey, if there's some weird stuff going on with your middle initial, or you've got a middle name, right? Or there's an initial put in, because programmers make a lot of assumptions about name when they're designing systems. So this works for a lot of cases. Then I find that. Otherwise, I just simply put out your grades and don't add in the stuff from Runestone. And that will result with a bunch of zeros. Fixable zeros, because there's a couple reasons this happens, right? One is you didn't sign up with the right email address and made a typo somewhere, or there's a typo in your name or something, right? There's a bunch of reasons why this might happen, but those occur so infrequently that once a student notifies me, that I can just simply add those in manually. right? That's like 1 or 2 people a semester, so that's not a big deal because the vast majority of you followed the directions I gave you for when signing up for Runestone. This took me about half an hour to write, and has resulted in, and I run it a few times every semester, which means that saves me hours upon hours of work every time I run this, because I can't just simply bulk copy paste from one file to another file. There's between students who leave the class, which Canvas will detect, but Runestone's like, it's not connected with with Canvas, so it doesn't know if a person's left. Or if people on Runestone accidentally make more than one account, right? So just by knowing a bunch of the stuff that I taught you or will teach you, right? This is just a little bit more, and this took me about a half an hour to write. If it was one of you, this maybe would take as long as doing the actual copy pasting it yourself. For writing something like this your first time around, but it's worth it. It saves me time every semester. Let's take a look at another fun example of what scripting will do for you, right? Of what kind of things we get. Classroom, intro. Let's see. Let's see. I want to think spring. Let's see. Summer 2018. Not here. ITP. Yeah, there we go. So I think maybe I would have been all over this in. I was teaching myself Japanese before I took a Japanese course here. And what I needed to do was, I was teaching myself using a program that was on Georgia Public Broadcasting called Irashai. So Irashai, Georgia Public Broadcasting. Okay, and it's basically designed for high school students. And the videos, at least at the time, the URLs look like this, where you have a video, very 90s kind of video, and each of these had an accompanying PDF, okay, for you to work on. Now, printing out and downloading each of these PDFs one at a time would take a while, right? I have a bunch of these PDFs, okay? But if as I go through these websites, I notice, wait a second, these URLs basically have kind of the same kind of format, and it's changed since when I wrote this, but it used to be that everything was located in this folder, at this URL, and what I did is I would just simply change the URL. I basically made a for loop to change the URL, and then what I would do is I would download that file using a library called requests, which just simply gets that, and I would say, hey, if the lesson is less than 10, I got to add a 0 to the PDF I'm trying to get, and then I would just download those. And I'd end up with like 74 files, which is the amount they have. And of course, though, that's a pain in the butt to write create 74 separate print actions, right? So I then wrote a separate script, which I don't know why that one is not there, but I wrote a separate script that would, hold on a second. I was just showing, okay, I don't know why it didn't save that one, spring 2018. sorry, I'm just looking for the most updated copy of this. This would have been. Where were you? Oh, here. So I had yet another script that what that would do would open up the directory and use a library called Py2PDF that combined all those PDF files into one PDF file. In case you're curious how long this took me, even though I had never worked with downloading PDF files and merging them together, I did have like access to the textbook, to a textbook I was using, the Automate the Boring Stuff textbook. This took me about 20 minutes. I did it while I was waiting to be called to my doctor's appointment. That's how long this took. Once you are comfortable programming and comfortable learning how to express yourself with programming, these kind of operations become really awesome and really easy to do and make your life a whole lot more convenient. Okay? Now, sorry, just wanted to wax poetic there a bit, I guess, about the usefulness of the stuff that we're learning. So, Hurricane Tracker is due tomorrow. Overall, again, if you need more time on it, you know, I understand, but we do want it done as soon as possible because it is very important for a lot of the stuff we do end up doing. You will want to watch on dictionaries. Thursday, I will basically be manually going over I will be lecturing about dictionaries. And then we'll start on the Hawaiian Pronunciation Lab. Okay. And I will adjust due dates of that and PIG as necessary. Last semester, PIG ended up being a extra credit assignment rather than a full assignment just because of the confines of the course, and we'll see what happens this semester. Okay. So, what are we going to do today? Well, I happen to have that on the modules list, which is we're going to learn about weird facts again, because that's when you take me as a professor, you're going to learn all about the weird facts. So this is in our Runestone textbook. It is all the way at the bottom of your textbook, which is, again, go to your textbook, scroll down. And this one is Project 11, Exploring Common Words in SETI. I will be grabbing something from a project we didn't do, which is Project 8, just simply because at one point it will ask us to graph it, and I will be referencing like last semester, where last semester's answers, so I can use that. So anyway, you can either access this via Spring 2026 Rosen, this link over here, or you can go to via Runestone directly. I'm going to go ahead and go to change course, Prof. Rosen. I'm going to go and just grab my code now so that there isn't an awkward transition later. Sorry, as awkward a transition, I guess. All right, so we are going to go to, I'm going to go to fall 2025. Going to go to Foundations, scroll down, SETI, Exploring Common Words in SETI. Okay, and now we are going to grab this one. Yep, awesome. I'm going to grab that code. I'm going to go ahead and do another paste just to make sure it does. I'm going to change the course back to Spring 2026. And then I'll paste that in so I don't have to do this in the middle of our thing. That way, all of you, and right now everybody's working on getting there, so there we go. Yes?
Where could I find it on Canvas?
Under Module 8, I believe, or yeah, Module 8 Overview Dictionaries. It will be here under Tuesday. So, what we're going to be discussing is commonality of words. Every language has kind of different fingerprints. Some have there's in anything using the Latin alphabet or anything based off the Latin alphabet, like English or French, there's a distribution of letters and the symbols that appear. In other languages, like anything based off the Chinese characters, they'll have their own frequency distribution of symbols, but there are also frequency distributions of the spoken word and language. There are tons of words, and some occur way more than others. We're specifically going to be looking at a list of the 5,000 most common words. This particular sample of data comes from the Word Frequency Data Project. They basically took 450 million words from magazines, newspapers, works of fiction, academic writing, and then did an analysis of it. So the title is what's the relation between basically the Exploring Common Words and SETI, which for those of you who don't know is this, which is basically the search for extraterrestrial intelligence. They are the people who point satellites at the sky and listen. But what are we listening for? How do we know what we are looking at is actually a signal of some kind and not some noise? How do we know? And the answer is we got to be able to figure out if it's a linguistics or a language or not. And if it's a language, as far as we know, it will follow certain rules for a complication, and that's called Zipf's law. That's one of them, at least. And if we go to the Wikipedia page, your eyes start to bleed a bit because it starts using weird symbols, right? And then we have a formal definition, which, right, where h(n)th is the normalization constant, the nth harmonic number, which of course requires another Wikipedia thing. But long story short, what it says is that when a set of measured values is sorted in decreasing order, the nth entry is often approximately inversely proportional to n. Or that means that basically the most common, or in terms of linguistics, the most common word occurs approximately twice as often as the next common. So their example is the word the in the English language occurs twice as often as the next most common word. Okay? The is a very common word. Okay? The next word in their corpus is of, which is 3.5%. And then and after that. So what we're going to do is we're going to basically look at this data set that kind of shows this. And what's crazy about this, the research that has been done on this, has shown that a lot of communication between animals uses Zipf's law. That doesn't mean it's the same kind of language, but communication in general between animals seems to have more frequent stuff. Right? Communication between birds, for instance, there's probably more often that you hear that they tweet out something saying, food here, looking for mate, or as opposed to danger, danger, we're going to die, being a bit less frequent, right? But those are all different things. If you have a pet, a cat or a dog, right, they'll bark or meow at you in some more frequent ways, but they probably have some way of notifying you and you hear it and you're like, oh crap, right? So, let's take a look at the data. And this is part of the reason I love Runestone. We don't have to download a file to work on this. The file is basically in the web page, and we're just going to use it. We're just going to straight up use this to do our thing. Okay? So we have a CSV file called words5000.csv. And we have rank, word, part of speech, frequency, and dispersion. I'll explain each of these. Rank is basically just which is by count, which is the most commonly used word. Okay? So the most commonly used one is the second most commonly used word is be, and fourth place is of, fifth place is a. To is listed twice, but that's because it has two different things, which is the part of speech. Okay? Part of speeches. We have A's, articles. So, the, and. Those words, right? Articles. Verbs. We know what verbs are. Conjunctions. Preposition for I. T is explicitly the infinitive to. To be, to run, to go, to slide, to jump. That to. The one that comes in front of a verb. Okay? P and D, I don't know what the difference between these pronouns are. That's fine. But that's basically all you need to know, which is that we encode the part of speech that they're in as well. Frequency means in the data set that they were using, how many times did we see this word? So the was seen 22 million times, whereas B was seen 12 million and was seen 10 million. Okay, and then finally we have this weird one, which is a really cool one called dispersion. And it's a rating between 0 and 1. And that's kind of how dispersed this word is among the entire corpus that they analyzed. Which is to say, is this a word that actually gets used, or is it only used in certain types of writing? Right? For instance, the word... So, for instance, the one they give is RE is fairly frequent, but it has an only 0.47 because RE is really only used in legal writing, right? This is like the word fracas, which is a noisy quarrel, but you only ever see this word in news headlines or in news. Nobody ever uses this in novels or parts of speech or anything like that. It only lives in news. Similarly, you're probably not going to find the term Big Chungus in, or Chunky Boy in academic writing. But if we're looking at memes and Discord posts or Twitch, you're going to get a lot of that, right? So, that's what dispersion is. It is the way we find language as across this stuff. And slang does become eventually part of speech. It just happens. Sorry. We're uncool like that, grown-ups. So anyway, we've got the CSV file, which has all of it. So what we're going to do is we're going to take this and we are going to store this into 5 separate lists. All right? So we're going to split these things into 5 lists. If we save and run, let me just go ahead and see if this is going to be coding. And it's been, a minute since we've coded, I'm sure. So let's just print foo, right? So let's go through this. So we need 5 lists. First thing I want to do is kind of open the file. Data is equal to open, and the file name is words, and I know this because it's told me, but it's up here as well. Words5000.csv. And I don't need to tell you that I'm reading it, but that's generally the polite thing to do, but I'm going to be simple. Leave it like that. We're opening up this file. And now I'm going to go ahead and I'm going to say, hey, here's all the lines. Lines are equal to data, not dar, data dot read lines. And that's going to just simply take all the data and dump it into lines, every line in there. We can print that out and see it. See? Although printing it out does reveal one of the things that we need to take care of, right? Which is that this first item over here is not information we need, right? It's the header. It's the legend information, right? Just like how you have a header in your Hurricane Tracker file. So to deal with that, to deal with the header, what we're going to do is we are just going to essentially toss it out, right? I've already stored everything in a list, so I'm just going to get rid of that first line in the list by saying, hey, the lines, what I'm going to do is I'm going to store something else in it. I'm going to store all of my lines from index 1, this entry being index 1, to the end. So this is just nice, concise ways to say everything but that first index. Make sense? Just slice it off like that. And now we've got the actual data. Okay? Now what we have to do is we have to iterate over this data and grab it. So it says we want to read the file and store the contents into 5 lists. So the 5 things we have are the rank, the word, the part of speech, the frequency, and the dispersion. Right? So we're going to create one list for each of these things because we are supposed to store all this information. I'll create a list called, and they'll start out as empty, rank, word, part of speech, which I'll call part. I'll call the frequency will be freak. And dispersion, I'll call disp, because that conveniently makes everything 4 letters long, and that looks visually appealing to me on a primal level. Yes? Oh. Here we go. So that's empty. Now we need to populate them. The way we are going to do that is with a for loop. So for every line, I'll say, 4 line in lines. Some of you will hate me for doing this. Some of you will think that's great. No worries. The specific I'm thinking of is 4 singular in plurals, right? It's only a single letter difference between those 2 words. So some of you will hate that. If you hate that, then just simply instead of using line, use L or use row or something else that's more distinctive. It's just a format that makes sense to me because I'm such a heavy English reader, right? There's no right or wrong way to do that, or to basically say, hey, this should be the variable. I just would not use I, though, because I is gonna implied as like an integer or the index. So I'll just use the singular. So for each line, what I'll do is I'll take that line and I'm going to go and manipulate it. I'm going to go line is equal to line dot split on a comma. Also something you're going to need to remember for the for your Hurricane Tracker. It's almost as though I had this planned out, that this should be done around the time of the due date of the Hurricane Tracker in case you're having trouble. So line is equal to line dot split. This takes any row that we read, and if it's separated by commas, if the fields are separated by commas, like this one is, right? Then it will take it, put it into an array. We'll print that out and we'll see what happens. Even though that's going to be a lot of printing, right? And it turns it into a list. Everybody see how that turned it into a list? Turned, right? Here, I'll even do you solid print line. So we're going to do the before the split, and then the after the split. You need to, right, and then print to nothing. And I'll get back to what I was just saying in a second. I just got ahead of myself. Run. Print. Why does it? Oh, okay. Never mind. Give me a second. Print line dot. All right, I know what's going on that's making it very upset with me. So first thing I'm going to do here is I'm going to say line is equal to line.strip to get rid of this thing. That's not really necessary. It's just only necessary for me helping you by printing it out and making it look nice. Got it? So you don't need to copy down what I'm doing. About those print lines in that strip are going to go away. But over here you can see the before we do our line dot split, right? This is before the line dot split, and this is the after line dot split. This is the only bit that I cared about. This was just simply getting it to render better. Same with this. This was to do a visual separation between the first line and the second line. Make sense? Okay. Split is awesome. We could work without it. It just wouldn't be fun because we'd have to do a lot of that stuff manually. Okay. So now that we've got our line split up into these 5 parts, let's go ahead and add those 5 parts to those appropriate things. So line 0, one last thing, the bit I said I would show you. You do need to have it as line is equal to line dot split. Whenever we do an operation on a string, we are not changing the string, we're creating a new one. We're creating a new string. So here, if you do this split operation or the strip operation and you don't save it, you're not going to be changing anything. Make sense? Okay, so, sorry about that. So going back to the only line we really need, now let's go and take a look at rank, right? The rank is the first index. So what we'll do is very simple, rank.append, and this actually physically changes the list, so we don't need an equal sign. Append line 0. This is a string, so what we're going to do over here is we are going to turn it into an int in the middle of adding it to a rank. Then we just send, let's see, part of speech, the word itself, dot append, that's a string, so we don't need to convert it, line index 1. Part of speech is also a string, append, line 2. Then we have the frequency dot append, which I'm able to remember because I've done this problem a bunch of times. That's where these variables are coming from. They've already been declared up here by me. Frequency dot append. This is a whole number, right? I can't count half of a word, so we'll do int. Sorry, I mistyped there, so now I fixed it. Int line 3, and then finally dispersion is a number between 0 and 1, so that's going to be a float. Dispersion dot append int. Okay, and then a float line 4. All right, and now we got to confirm that this works by and I'm going to do that by printing out the word list, and then I'll print out the frequency list below that and see if those match up to our expectations. And they should. The, B, right? 22 million, 12 million, 10 million. All right. Now, before we go on, I want to show you a really cool, nifty trick. Okay, that is kind of Python specific. You will not be tested on this trick. You are not expected to know this trick. I just think it's really cool. Okay. If I wanted to print out everything together, like words, the frequency, all the rank, the word, the frequency, the part, all that stuff on the same line, right? I would normally have to do something like this, which is for I in range, right, rank, length of rank, And then what I'd have to do is like print rank index 0, comma, word index 0. Okay. Not 0, but I, index I. And this allows me, and you'll see what this prints out, right? It prints out each of these, the rank of the word and what the word is. Program was interrupted. Okay, stop. There we go. Okay. I want this to be just a bit bigger. Okay, now though, is there an easier way to go through this? And I'll show you that easier way, because that's the kind of question you only ask when there is. For thing, let's find out what thing is, in zip. Well, that's an interesting word. Zip, rank, comma, word, print the thing. Whoops. Really? Misclicked, and so it erased my thing. Print for thing in zip rank word print the thing. And we get a tuple, which is like a list, but it prints out basically everything in index 0 together, then index 1, then index 2, then index 3. It allows you to group. Zip allows you to zip up a bunch of things together. So I can add freak to this, and now that will get printed out alongside them. And it's super easy, super convenient way to print, to kind of iterate over multiple items of the same length all at once. Make sense? Okay. Bonus, a XKCD many of you on liberal arts campuses may enjoy. So again, talking about linguistics. Linguistics do change over time. And this is what we call a log graph, where if you're familiar with the Richter scale for earthquakes, where basically you have a 9 to a 10, right? That generally means, I think it's 10 times as powerful to go up a single digit on the Richter scale. So over here, the y-axis, it's 1%, 10%, 100%, 1,000%. It's multiples of 10. So it's not doubling, it's even more. The frequency of the use of the word sustainable in the English text as percentage of all words by year, with the year on the bottom. And we see that basically over time, the word sustainable has become more and more of our lexicon. It's become more and more of our vocabulary. But if we extrapolate this rate of growth, by 2036, sustainable occurs on average once per page. 2061, sustainable occurs an average of once per a sentence. And by 2109, all sentences are just the word sustainable repeated over and over again. This is also why making an extrapolation is kind of dangerous. XKCD extrapolation, which is one of my extrapolating. My hobby, extrapolating. Yesterday, today. As you can see, by the late next month, you'll have over 4 dozen husband. Better get a bulk rate on wedding cake. Right? Because it's extrapolating from a small sample size. Right? Some things are just done for humor. All right, Zipf's law. So we want to examine kind of the idea here that what fraction of usage the top 10 words most represent. So the first thing we need to do is we've got to take that frequency count that we have and turn it into a percentage. Okay, so calculate the total the top usage percentage for the top 10 words in the list. Store this result in a variable called top 10. Same time, calculate the percentage for bottom 10 words on the list and store that in bottom 10. So what we're trying to do is figure out how often these words are used. Percentages are essentially fractions. And so the way we can calculate those are, well, first we need to grab a bunch of this code that we already made, right? Which is all of this code. Whoops. Oh, and let me share this code with you. We're going to grab all this code that we made from the last one. And what we're going to need to do is we're going to need to calculate essentially the percentage for each of these words. Yes?
I'm getting an error that my line is like out of index, but I have the same exact code.
I'd have to take a look specifically. Which line is it occurring on?
It's occurring on line 12, so like where word dot in.
Line 12, you say. So over here?
No, mine's 14 on
So word.append line 1?
yeah.
And you did this line is equal to line.split, not lines is equal to line.split?
Yeah, line is equal to line dot.
Okay, and that goes off without a hitch. So rank, and the rank.append works, you said.
The rank dot append works without the int.
It will work without the int, but
For
when
some reason it says that the type is wrong if I try to do it.
interesting, that type shouldn't really matter there. I'll have to take a look at it. I did share the code, so you can refresh your screen and see if that helps. So let's see. We need to figure out what amount these most common words make up of the most common 5,000 words. So we're going to do that by basically saying, hey, the total of all the words is equal to the sum of the frequency. We're going to just take all of this field and we're just going to add it up. Print total. And we find that in total we counted 329 million words, okay? So figure out what percentage any specific word is of that. We would just take that and divide it by total. So let's go ahead and create a new list. I'll go ahead and do something called maybe percentages is equal to that. And unfortunately, we can't do this until we are done adding everything up. So what we got to do is we got to say, we got to do our totals equal to sum of frequencies, as we had just a minute ago. And then for f in frequency, then what are we going to do? We are going to say percentage dot append, and what we'll do is we'll say that is, just trying to figure out the best way to present this. Yeah, it will be a number between 0 and 1, so that will be frequency, f divided by total. Print percentage. So if we do that, we'll see that we have 0.066. So in other words, 6.5% of the time we have 6.5% of the time we get the word the. So, or rather, the accounts for 6.5% of all the words we counted. Okay. I feel like this is a very different way than I've done it in the past, but oh well. So it's asking for the top 10. So the way we do that is actually fairly straightforward. We're going to use the sum again, only we're going to do a slice because slices are awesome. Top 10 is equal to, we're going to take the first 10 there, we're going to take the first 10 of these. And normally it would be blocking off time for you to try these, but we're just back from break. I figured you probably want me to walk you through this so that you said to get us back into, the swing of things. So top 10 is equal to sum, again, also an awesome thing, of the percentage. And well, first off, if we sum up percentage and don't do anything with it, we're just going to get something close to 100%, hopefully. Yep, see, actual value, and we're expecting to get 27%. Right? Makes sense that summing up all the percentages adds up to 100%. So, or 1 in this case. So for the top 10, well, since they're in order, this gives us from index 0 up to, but not including index 10, it's the first 10. So if we just add those up, boom, we get something close to the actual value, to their expected value, but they're only checking those first 3 sig figs. 276. So let's go ahead and now do the bottom 10 because we can just do that in one line as well, right? Bottom 10 is equal to the sum of the percentages, but we need the last 10 things. That's another slice. Negative 10 to the end. Right? Negative 1 gets you the last thing. Negative 2 gets you the second last thing. Negative 10 gives you that one. So bottom 10. Whoops. Did I not? Oh, I just called it boom 10 because I was in the middle of talking, and apparently I'm just not very good at typing and talking at the same time. You'd think I would be at this point, but no. Okay. So the top 10 words of the English language make up 27% of our entire language or linguistical content, whereas the bottom 10 of these 5,000 numbers 4,991 to word 5,000, they amount to combined 0.015%. 0.015% of the English language. So for just kind of comparison, what are these words? The top 10 words are words like the, be, and, of, in, to, have, to, it. Those are our most common words in the English language. Whereas the bottom 5, this is our bottom of the 5,000, are things like censor, laundry, manual, pistol, naval, plaintiff. And we can see there that's got a lower dispersion because it's used outside of legal writing, but it's primarily confined to legal writing. Kid, you'd think that would be a common one, but it's saying kid as a verb, I kid you not, right, is not that often. Middle class, apology, and till. Right? So words are extreme. So some words are very very common and some are not. Okay. I'm going to share code again. Now, for the last bit, I'll be showing you some graphing code. Python has some of the best graphing libraries available. Matplotlib is the one I go to, but this textbook, due to being able to encode it in the web page, uses a library called Altair. It's not very important that you know how to use it. Just hopefully you can read what I'm doing at this point. But one of the important things to understand is that when we're dealing with graphs which have such huge dispersions in these values, such discrepancies in these values, that the y-axis being the y-axis, like a unit axis, does not always make sense. Okay? For instance, here's another XKCD comic. Log scales are for quitters who can't find enough paper to make their point properly. Fuel energy density in megajoules per kilogram, and it compares sugar, coal, fat, and gasoline, which are all 10-digit numbers, but uranium here, sorry, not 10-digit, 2-digit numbers. Uranium here is in the millions. Sorry, tens of millions, 76 million megajoules per kilogram. Very, very energy dense. And so a lot of times for this data, because of these discrepancies, we do use something called a log scale, where the y-axis, as we see here, is not basically, you know, oh, it goes to 0.1, 0.2, 0.3, right? It's not unit-based. It's instead logarithmic, meaning we're going up by multiples of 10. Okay? Or we are taking a number and throwing it in a logarithmic function. I know a lot of you kind of get scared when we hear the term logarithmic. Right. This is because your math professors and teachers in high schools were probably not necessarily taught the appropriate way to do logarithms. Logarithms really are not that scary, though, if you think of them as in terms of an operation and completely forget that whole relationship between exponents, right? I don't even bother with remembering that equation. That's useless for me as a programmer. I don't use that as a programmer. I use a log as an operation. A log simply asks you, how many times can I split this into piles, into evenly sized piles? For instance, log base 2, 64, asked me how many times I can take a pile of 64 things and split it in half. So 64 can be split into 32, into 16, then into 8s, then into 4s, then into 2s, then into 1s. I can't split it any further down into 1s. The answer is 6. That's a useful thing that's how logarithms are useful. Same thing for log base 3. That's just asking how many times I can split it into thirds, right? For instance, 27, I can split I can split that into 3 piles of 9. I can take those 9, split them into 3s, and those 3s and split them into 1s. That's a logarithm. That's all it is. I don't know if they teach that in math curriculum these days ever since the Common Core got updated. I found the Common Core is teaching a lot of things that I had to teach myself, which is great. But there's still a lot of focus on that relationship between exponents, which, while being important, is not necessary for programmers. We use logarithms when we basically write algorithms that basically half the amount of search space you have each time. So the reason for this is that if we take our data that we had over here, and I am just going to comment out the bit with the logs, and we'll put that in a bit. Okay, I'm going to graph these and run it. Okay, I'm going to take our information and I'm going to graph it, and then I'll go through the code. Right, if we graph the rank of the word to the frequency, right? We get a bit of a useless graph. Okay? Here is rank 4,000, 1,000, 2,000, 3,000, 4,000. They all look at basically that they're basically in the same place, right? Make sense? Whereas the frequency, we can see that it just sharply shoots down after the first few letters. So this graph, where we're just graphing the rank against the frequency, okay, is useless. And that's literally basically just letting the rank be the x-axis and the frequency be the y-axis. That's all this is. Okay, and if we just simply graph that point by point and then draw a line between each of them, that's what we get here, right? If we actually were able to zoom in, we'd end up seeing something a bit more jagged, obviously, but that's what we have there. So the way this works is that we've got the exact same code we had, except I do 2 imports here. We aren't using math yet, the math library. We do our reading of the files. We do our appends as normal. Okay? The appends are no different here. We'll be changing that up in a bit when I comment those out. Then over here I do the graphing, which is only taking me 5 lines. I say, hey, we're going to create a Altair. We're going to make it data. We're going to create a new graph. I want you to get started by loading up a bunch of data. The data is we're going to have a field called ranking, and that's going to be equal to the rank. And we're going to have a field called frequency, and you want to grab the values from Freq for that. I find this way of doing it weird, but it works, so I don't question it. Again, I don't use Altair all that much. I use it once a semester, in fact, this lecture. Altair, chart, data, saying, hey, we're going to make a chart from this data. I want you to take that chart, this graph of sorts, and the way I want you to mark it is to draw lines between all the points I've defined. And those marks, the X should be the ranking, and the Y should be the frequency, and then please show it, because if I don't have this line, I'm not actually going to show it. Okay. Now, what we're going to do instead is we are going to take the frequency and we're going to throw it into log base 10. Okay, math.log function. We're going to take that function and throw it into the log function instead of just giving it to me naturally. And we're going to end up with these values instead, you'll see. The values of frequencies are between 0 and 8, which is a bit weird, but let me explain and now it makes sense. This is because we just did a base 10 operation. This is saying 10 to the what power? So over here we have 10 to the 7th power, right in between. This is 10 to the 6th power. The frequency. So because we've done each of these is now basically a power of 10. So 6, then 5, then 4. Since each is now a power of 10, we can kind of zoom in and see, oh, it's not cratering to 0 as quickly as it used to, right? So, and this is the bit that basically will make scientists really excited, where basically if we take the x and y axis and both, okay, and do this logarithmic operation to both of them, where if we get something that looks like a straight line, it gets really exciting. Because it's basically saying, hey, we can visually see the important things are really important. And then we can see basically that as we go on, the things of lower rank become less and less important. But we can see that we've got something approximating a straight line. Words are apparently hard after a break. And this is fairly exciting because it gives predictive power. Straight lines give us predictive powers. But since these are powers of 10, we can also just look at the data over here, and we'll see that phenomenon. And if we actually just look at the data and use our brains for a second, we can see this phenomena in action, where we were saying that words basically occur twice as often as other words. And that's not a bad approximation. 22 million versus 12 million. That's close to half. Then we drop down to 10 millions over here, but then we have 7 million. So we can see that there's kind of a halve over here, a halving almost between these two, and then we've got a clump here of things that occur about the same amount of frequency. And then we've got another clump that's close to half. And then another clump that's close to half. And we see that basically, 25 to 2.5 million to 1.9 million. And then we've got, and then it just keeps, we see that. It's pretty crazy. I don't know why they don't always go in order, though. I feel like these two are out of order. But, yes?
So how come some words have like a lower frequency and a higher rate?
So have two rankings?
Like, if there's a lower frequency but a higher rate.
I'm not sure. I always assumed that this was in order, but I'm seeing like things like this. Maybe it's the part of speech that wins out when they're close, right? Maybe it's an equation between, maybe the ranking is a function of, that's probably it. The ranking might be a function of their, oh yeah, the rank is an order, the rank order is a function of both frequency and dispersion. So I assume that means that, but basically that you're just gonna, is that you take the frequency, rank is determined by, I guess frequency multiplied by dispersion, I would guess. And that would explain for the discrepancy why this number at 0.99 is higher than this number at 0.95. So that would explain why also we don't get that exact halvening, right? That makes a lot of sense now. In fact, we can, why don't we go and actually take a look at that? That seems like a great thing to take a look at. Everybody blame him. No, I'm sorry. All right, so I just can't help it. When I see data like this, I get curious. Lines in, so for each of these lines, what we'll do is we'll also create a, what we'll do for rank, rather than calculate the rank, I'll calculate the score that went into the rank. So what we'll do is we will do, I guess, frequency. We'll do this. Let's see, multiplied by this. Line 4. And then we will print, and then 4 are in rank. Print, actually 4 S in zip rank freak dispersion, print S, and now there we go. So we see, yeah, we're starting to see some stuff now. So we see about a halvening over there, then another close to that. But now all the numbers appear to be in descending order. Okay, that's interesting. Andrew's Guns and Ammo, if we can't kill it, it's immortal. Hello? No, I'm in the middle of teaching class. Thank you very much. What's the point of power if you don't have fun with it? All right. So this is now in order. So now we see, so this also explains like the jaggedness of this line. So what we could do then is rather than doing the frequency over here, we can, I guess we could create a new one called score is equal to score is equal to this. And then what we'll do is we will do rank frequency dot append. And what we'll do is we'll do score is equal to, and I'm going to be a bit cheeky here, freak -1, sorry, score is equal, sorry, score dot append. Oh my gosh, spell. Freak -1 times dispersion -1, which are the values that we just, oh, that's not going to work. Nah, it's not going to work, unfortunately. No. Gotta do, oh. No, it will work. Freak -1 times the dispersion -1. Okay, that gives us our score. Okay, and then we are going to throw that into our and then I'll fix that into the logarithm function in a minute. So ranking will still be the same. We'll take this and called scoring is equal to score. And then we have to call this scoring, otherwise. Okay. And then, right, we get much less jagged over here. But again, we're back in the in our what I called the useless case. So now we have to do our logarithmics. Sorry, our adjustment to make it logarithmic. So frequency, rank. Oh, no, we don't need that. And so now over here we'll just add math.log. So this will throw the logarithm function at it, and we want to specify that it is base 10. Woo. That's a lot less jagged, I think. Frequency times dispersion base 10. Yeah. Maybe it has a bit more trouble in the end. It could be that, like, it's the square. It could be something like dispersion squared, right? Or the score squared times dispersion squared. That might be a way to do it. And then take the square root of that, depending on it. You can mess with data like that, and it gets very interesting very quickly when you start messing about with data. But that's what you do. You look for a relationship of some kind like that by messing around with data. Once you see that the data looks like this, you can start, again, extrapolating values. We see that stuff is roughly twice as, that one category of words is roughly twice as important, which is important. It allows us to detect signals from noise, right? Anyway, right? So let's see. Yeah, it's 3:17, so that's enough for the day. On Thursday, I will share. Sorry, let me share this with you so So the way you can get credit for all these is very simple. I share this code with you. You run it, and you get credit. So be sure to do that and to fill out the questions at the end saying, hey, how intense did this feel? On Thursday, it will be a standard boring lecture by me where I will just simply be going over dictionaries, which are really awesome, really powerful tools, and we're going to see we can do a lot with them. All right, take care.